Yeah, questions are welcomed. Mr. Bear, did you ask a question? Is it Mr. Bear? Okay. Who never asked a question? Robert Saylor, did you ask any question? Oh yeah, you are supposed to ask question. Okay? No question yet?
No.
All right. Okay. Okay, let's go to the switch capacitor filter. Yeah, before that, say for the active RC second order bandpass filter, say we have some parameters. Say center frequency is f0. It means my omega 0, which is 1 over RC, is 2 pi times this f0, 1 megahertz. Yeah, if my quality factor is 10, my bandwidth, Q is 10. Q is 10. And then my gain is only 2. Yeah, should be minus 2, right? My gain is minus 2. Minus G, actually. Let's see. Yeah, actually, we have a freedom. Because, see, here, see, I know F0, this is 2 pi times, this 6.28 times 10 to the 6 radian per second. But I have RC product there, right? So I just put C equal 1 pop. C equal 1 pop. Then I can calculate resistance, right? That resistance is calculated to be 159 kilo. And then this is a QR, or 10 times, 1.59 mega ohm. Okay, this is R times G of Q, right? Is this right? So R times, is this right? No, Q of G. Sorry, Q of G, right? R times Q of G. So 5 times, bye-bye. 796 kilo. Okay? This doesn't matter. So this will consume too much current. I can just say 100K. 10K consumes too much current. Then, if I take output from here, this should be my bandpass filter. Okay? Any questions?
네, 저거를 스위치 캐패시터로 바꿀 거면은 스몰 R을 그냥 캡을 빼면 될까요?
Okay, the question is, see, if we want to change this one into a switched capacitor filter, so this can be implemented easily by using a switched capacitor gain stage, right? Yeah, that can be done, but that's no good. Because if I switch the sequence of switches, this -1 can be implemented easily. Then we can save 1 op amp. Okay? So we want to implement this switch capacitor filter by using 2 op amp only, not 3 op amp. Huh? Yeah, op amp takes a lot of power and area. 2 op amp is better than 3 op amp, right? No? You don't agree with that? Huh? 2 op amp less expensive. Okay. Yeah, we want to convert it into switch capacitor filter. Then see all those resistance, except this, all those resistance R1, QR, R, those 4 resistors are replaced by switched capacitors. Okay, you know, the equivalent resistance is P over C, right? We want to find this C value for the switched capacitor. Yeah, because my center frequency is 1 megahertz. I want to use 10 megahertz clock signal for switch capacitor. Then my period is 100 nanosecond, right? Oops. Oh, how come? 100 nanosecond. Then my C is just 100 nanosecond divided by R. Okay? Then I can easily find my capacitors. Okay? This may be 0.6 pop or whatever. I'm not sure exactly. Something like that. So if I put 159K, 100 nanosecond, yeah, around 0.6 pop, something like that. Okay. Any question here? Nope. Okay, let's convert it into switched capacitor. Oh yeah. Actually, this is the one. Before, yeah, this is a simulation result of active RC. Active RC. See, yeah, I used this op-amp. This is only 1 millisiemens. So my gain will be, see, because I have a 159K loading, this GM times 159K will be, my gain is 159, right? So my gain is rather limited. Because my op-amp gain is only 159. That's not very large. Only 40 decibel. Maybe 43 decibel, something like that. Okay, anyway, so I have some result here. This is my frequency from this 1 megahertz. This is 10 megahertz. 10 megahertz there. This is 0.1 megahertz. So I have a peak here, right, around center frequency. Here, see, my center frequency is slightly different. I want 1 megahertz. My gain is slightly different. How come this is different? Gain error. Because my gain is small, right? If we increase the gain, this will be improved. Is it right? Oh yeah. This is the one, the same thing. So if I increase gain, I think, what is this thing? Oh, okay. This is for small gain. Yellow one is a small gain. Red one is a large gain. For the large gain, my center frequency is 9.0 here. This is large gain, close to 1 megahertz, right? Small gain, much smaller. Yeah, quality factor is 10, designed to be 10. So with a large gain, it's a 9.96, close to 10. With a small gain, my quality factor is only 9.16, smaller, right? Center frequency shifted. Gain is smaller because of a small op-amp gain. Questions? No. No question. What is this thing? Oh yeah. Because this is a bandpass filter, right? I put 1 megahertz, yellow one, and 800 kilohertz, 0.8 megahertz, red one. So for the red one, I think the input amplitude is 0.1 volt sine wave. Eh? Then for the 1 megahertz, output swing is around 3.2. Yeah, expected, right? Because my G is -2. So it's around twice. With 800 kilohertz, the amplitude is swing is 0.0884 volt. Yeah, much smaller, right? So it works. After some transient, like what's this? 100 microsecond, is it? 10 microsecond. With a transient of 10 microsecond, it settles. So yeah, it has a peak at 1 megahertz. 800 kilohertz, it has a much smaller amplitude. Okay. My active RC bandpass filter works well. Okay, let's try to convert this one into switched capacitor version. So I decided my cap is 0.6 pop. This thing is 5R 1.62 pop around, right? Yeah, this is QR. Ooh, Q is 10, right? 0.06 pop, something like that. So I will replace this one by a. I will replace this op amp. Okay. Okay. Yeah, this one. See, I want to make it auto zero version. So I want to make auto zero the switch capacitor integrator. Then how can I make it? Yeah. Okay. Yeah, the first one is one pop. This is C, and then I need a by 2 offset sampling switch, and then this QR register can be implemented by a capacitor by 1 by 2. This is a QR. Yeah, maybe 0.06 pop or whatever. This thing is 0.12 pop, something like that. Okay, so this is my Vout. And then I can implement very easily for the next one also. Oops. Huh. This is auto zero the capacitor. So actually I want to make it into V2. So I must be careful in the switch selection. What is this thing? This is 0.6 pop. This is 1 pop, right? So, but here I want to make an inverting integrator. Okay, inverting. How can I make an inverting integrator? I should be careful. So here, see, I will put. So this is same as that by 1 by 2. For this one, I will put by 1 there, and then by 2 there. Then this is inverting integrator. See, my V2 is only plus omega 0 of S VO. Okay. How come it becomes inverting integrator? If you look at this one, see, during by 1 phase, it stores charge, right? because by one base this switch is on, so it this 0.6 pop capacitor samples this V out and also the input offset voltage, okay? And then during by 2 phase, so this by 2 phase 0, this minus Q charge is pushed into here, plus Q charge will be developed there, see V2 will be positive, right? Yeah, here see during by one phase, see this is on, this develop, see by one phase this is on, so minus Q, this minus Q, because minus the charge will be developed like that during by one phase, right? So this VOC is minus Q. It is an inverting integrator, okay? But here it sees V2 sees plus Q. So it is a non-inverting integrator, okay? Question?
파이 4페이지 때 파이 1에서 저 마이너스 인풋 쪽이던 마이너스 Q가 1피코 저 Q4로 푸시 이러니까
Okay, your question is what is the push mechanism? Say, let's just see. So we'll see our non-inverting integrator. Non-inverting integrator looks like that. So I have a capacitor here, and then I have a feedback switch there. So minus positive. So this is 0.6 pop, 1 pop there. So this is by 1, this is VO by 2, by 1, by 2. So they are changed, right? Their places, by 1 and by 2. Okay, so during by 1 phase, what happens? Okay, by 1 phase. So this is on, so this becomes my input offset voltage, okay? Because of feedback switch by 1. Then, you know, this charge, this plus Q minus Q will be developed there, okay? This Q will be VO, this 0.6 pop, VO minus input offset voltage, okay? Yeah, during by 2 phase, what happens? So this is on, this is off, this is on. Then it will go back. This charge will go back to this input offset voltage, like plus. Is this plus? Yeah. Plus. This will be minus, okay? Then the difference of this charge will move here, okay? So difference of this charge is what? Minus Q minus 0.6 pop BOS. This will move here. The same amount of charge will be developed there, right? Because this charge current flow will generate the same current flow here, right? The same amount of charge will develop on the right hand side of this 1 pop capacitor. Okay. Then my V2 Tn will be my V2 Tm minus 1 plus this Q plus 0.6 VOS divided by 1 pop. Yeah, this will be added, okay? Yeah, this is only, you can see, this is only 0.6 pop divided by 1 pop of VO, right? VOS term will be dropped, all right? So it is because this is positive, this is only non-inverting integrator. Oops. Non-inverting integrator. All right. Question? No? This switch connection is a little bit, we must be careful about this switch connection. This switch connection is a little bit complex. We'll talk about that at the next class. Okay? Yeah, let's start it.